Welcome to the deep dive. Today, we're zeroing in on something foundational. The chapter on motion from Richard Feynman's Lectures on Physics.
It's chapter 8 in volume 1. And Feynman, well, he has this knack for starting simply. You think, okay, motion, a car moving, easy.
Exactly. Then he immediately flips it and shows you how incredibly difficult it is to be precise about it. What does moving right now actually mean?
So our mission today is to trace his steps, right?
Right.
Follow his logic from just observing something, change position.
All the way to the core mathematical tools you absolutely need. Calculus. We want to unpack kinematics, the description of motion, just like he does.
Stick strictly to the source, yeah. Position, velocity, acceleration, and how they're all connected.
So he kicks things off with the basic idea. Motion is change in position over time. Simple enough.
But then comes the measurement challenge. He's that first example, the car on a road. One dimension, nice and easy to start.
Right, and there's that table 8.1 in the text. It shows the distance traveled at 1-minute intervals. Time 0, distance 0. After 10 minutes, it's gone 24,000 feet.
But the crucial detail, like you look at the numbers, is that the distance covered each minute isn't constant at all.
No, not even close. 1 minute it does maybe 6,000 feet, the next maybe just 500. So it's speeding up, slowing down.
Stopping, maybe. And that really highlights the problem. We can calculate the average speed over a minute, easily distance divided by time. But what about the speed at the exact instant the driver slams on the brakes?
That average tells you almost nothing about that moment, which is why the second example, the falling body, is so important.
Yes. Much cleaner mathematically. Here, the distance fallen, $7 is just proportional to the time squared. $7 is equals 16t222.
So predictable. The text shows at 1 second it falls 16 feet. At 2 seconds, 64 feet. It's clearly accelerating.
And because the speed is constantly changing, we bump right into that age-old conceptual problem.
Okay, let's unpack that. This whole idea of instantaneous speed. Feynman brings up Zeno's paradox Achilles and the tortoise.
Right. And it's not just a historical footnote. It really frames the philosophical puzzle that calculus eventually had to solve.
The idea being you can't ever actually reach the tortoise because you always have to cover half the remaining distance first, and then half of that, and so on forever.
Exactly. It suggests motion itself is kind of an illusion, or at least impossible to describe moment by moment. It seems like you're always stuck between points in time.
So forget philosophy for a second. Practically, we define average speed as distance over time. But, like the example, telling a cop your average speed over the last hour...
He doesn't care about the last hour. He cares about the speed on his radar gun right now.
So we need the speed at one single instant, a moment with theoretically zero duration. How do we even approach that?
Well, this is the clever move. Instead of looking at big intervals like a minute or a second, we look at incredibly small time intervals. We call the interval delta t dur.
Okay, delta t. But wait, even if it's tiny, it's still an interval, right? We're still measuring between 2 points in time to find the speed at one point. Feels like we're still fudging it a bit.
But that's the beauty of it. We calculate the average speed over that tiny interval, delta t. So small distance change over small time change.
Okay.
And then we ask the critical question. What value does this ratio, this average speed, approach as we make that time interval delta t2 smaller and smaller, essentially shrinking it down towards zero?
So we're not actually dividing by zero. We're looking at the trend, the value it gets infinitely close to.
Precisely. We're taking the limit of that ratio as delta 2 approaches zero. That limit is the instantaneous velocity, v-voller.
So mathematically, that's v delta t to zero.
That's the formal definition.
Yeah.
It's the heart of differential calculus, developed by Newton and Leibniz to solve exactly this kind of problem.
Right. Writing out limit as delta t approaches zero every time seems cumbersome, though. There must be a shorthand.
There is. The notation is simply c del tt.
dsdt.
Or dst basically means take the derivative with respect to time of whatever function follows it, in this case, the position function, $2. It packages that whole limit process.
Got it. So now we can use this powerful tool on the falling body example, where c s and t2 put o. What happens when we apply a deta to that?
Well, the rules of differentiation, which Feynman derives, tell us that the derivative of 16 put o with respect to 2 is 32 times ago. So the velocity is v 32 times.
Wow. Okay, so we went from a description of position to a precise formula for instantaneous velocity.
Exactly. And now finding the speed at a specific moment is trivial. What's the speed at exactly 5 seconds?
Just plug it in. $5 is 32 times, sometimes 5 is equal to 162 feet per second.
No averages, no approximations needed. That's the power of the derivative. It gives you the instantaneous rate of change.
The source also shows this works for more complicated situations, right? Like if position was d to at3 plus bt2 plus ct plus d.
Yeah, it demonstrates the general method.
Right.
If you were to calculate delta S delta TT for that,
Yeah.
using the limit definition, it looks messy at first. You get terms with delta t to 2, etc.
But that's the magic of the limit again, isn't it? As delta t goes to 0.
All those terms involving delta t2 just vanish. They become 0. The derivative rules essentially automate this process.
And you're left with just $$ equals ds dt equals 3at2 plus 2bt plus ca. The constant dollar disappears too because it doesn't change with time.
Right. The math elegantly handles the concept of instantaneous change.
Okay, so differentiation gets us from position to velocity. What about the other way around? If we know the velocity at every instant, how do we figure out the total distance traveled?
The inverse problem.
Yeah.
If we know the rate, how do we find the accumulation?
So instead of breaking down the motion, we're building it back up.
Exactly. Think about it this way. Divide the total time into a huge number of tiny little intervals, delta t again. During each tiny delta t, the velocity v is almost constant. So the little bit of distance covered in that tiny time is approximately vd times delta t.
Like calculating distance 8's time for a very short period. A tiny little piece of the total distance.
Right. You get all these tiny distance proceeds. The total distance is just the sum of all those tiny pieces. We write that sum using sigma, some vd times speed.
But again, that's an approximation because vd isn't perfectly constant even over a tiny interval. So we need the limit idea again.
Precisely. To get the exact total distance, we take the limit of that sum as the time intervals delta t shrink to 0. This limiting process of summing infinite tiny pieces is called integration.
And the symbol for integration looks like a stretched out S, right?
Yeah,
For some.
exactly, the integral sign. So the total distance is vtt dt dk.
So differentiation takes you from Zalt to Te, and integration takes you from back to Solar.
They are inverse operations, fundamental theorem of calculus, essentially. That's the core relationship.
Okay, so we have position, and its rate of change is velocity. What about the rate of change of velocity itself?
That brings us to acceleration. It's defined in exactly the same way. Acceleration is the rate of change of velocity with respect to time.
So just like $y equals ds dt, acceleration is a20 equals dv dt?
Correct. And since the on dollars is already the first derivative of CA, must be the
second derivative of position, $6 with respect to time. How do we write that?
The notation is 1 is a 1 equal dtt2 is dt2. The squared notation indicates differentiating twice.
Okay. Let's apply that to our falling body. We found 1v32t. What's dv dt?
The derivative of 32 twos with respect to TO is just a constant, 32.
So the acceleration is a 302 feet per second. It's constant.
And that constant, 32 foot second, is what we usually call d to r, the acceleration due to gravity near Earth's surface.
And the source points out that when acceleration is constant, like with gravity here, things simplify nicely.
Yes, the integration and differentiation lead to those two classic kinematics formulas you learn early on. Velocity v, Valerie is starting from rest, and distance, Vol.1 t2.
So those familiar formulas aren't just pulled out of thin air. They are direct consequences of applying calculus definitions to constant acceleration.
Absolutely. They're built on this calculus foundation.
Now, everything so far has been kind of one-dimensional. Along a line or straight down? What about the real world? Motion in 2D or 3D?
Right. Things rarely move just back and forth or up and down. We need $6 and 6 coordinates.
So does all this calculus stuff just break down?
Not at all. This is where vectors come in. But the core idea, as Feynman explains, is remarkably simple. You just treat each dimension independently.
Independently. How does that work?
The motion in the x direction depends only on the forces and velocities in the x direction. Same for y, same for z. So the velocity component in the x direction, $6t, is just dt.
Okay, so Fidonis doesn't care what phi or v are doing when you calculate it?
Exactly. You find c ball skill d eats dtt, ev dt, and phi d dt separately using the same calculus rules.
Then how do you get the object's overall speed, its actual speed through space?
You combine the components. Since they're perpendicular dimensions, you use the Pythagorean theorem, just expand it to 3D. The total speed 5dd is underscore d v by 2 plus v2 plus vz2.
Makes sense. He uses that classic projectile example, right? Like firing something horizontally off a cliff.
Perfect illustration. The horizontal motion has 0 acceleration, ignoring air resistance, so the x is just constant.
Okay, constant speed sideways.
But the vertical motion has the constant downward acceleration of gravity, d. So Vira changes according to d equals change of g do. So you have simple constant velocity motion horizontally and simple constant acceleration motion vertically happening at the same time.
Exactly. And when you put those two independent motions together, what path does the object follow?
A parabola, that curved trajectory we always see. Right. The complex parabolic path emerges naturally from combining two much simpler motions, each described perfectly by our calculus rules for c's and phi in the dollars.
So looking back at the whole chapter then, we started with just watching a car move and immediately ran into Zeno's paradox, this deep problem about describing an instant.
A problem that wasn't solved by better stopwatches, fundamentally. It required a whole new way of thinking mathematically.
Calculus, differentiation, and integration. That seems to be the absolute core message.
It is. Describing motion precisely hinges entirely on these twin tools. Differentiation lets you find the instantaneous rates, velocity, accelerate, from the overall motion position.
And integration lets you build back up, finding the total change distance from the known rates,
Yeah.
velocity or acceleration.
The key takeaway is really that deep relationship. Position dollars a dollar, velocity of dollars, and acceleration, a dv/dt, which is also 2s dt2 and 2. Understanding kinematics is understanding how calculus links these three.
It really makes you think, though. The source shows how these mathematical rules discovered centuries ago, seem to perfectly describe how things actually move, from a falling ball to, well, presumably planets.
Hmm.
What does that tell us, this perfect fit between abstract mathematics and physical reality? Is math just a description we invented, or is it somehow the underlying language the universe itself speaks?
That's the kind of question Feynman often leaves you pondering. Something to think about next time you watch something move.
Indeed. Well, thank you for joining us for this deep dive into the very beginnings of motion, according to Feynman.